I'll try to share my screen. Second. Do you see the presentation?
Yes, we see the presentation.
Okay, so let's start. Thank you for inviting me. I'm very happy to present here my work on my group to this workshop. I am Jonathan Kakake. I am assistant professor here in University of Naples, and as already said in the introduction, I also collaborate with also other technology partner and several research projects. So what we are going to see today is how to use or how we use aerial machines to perform this kind of testing that is called non-destructive tests. So just a brief look at the agenda. I want to introduce, of course, my research group here in Naples, in which we are working very hard in inspection and maintenance activities. Then just a few words on what is an aerial robot and what is the aerial manipulation. Then we can move directly on NDT measurements, and in particular, just focus on a particular branch of this kind of field, that is the inspection and maintenance of oil and gas facilities. So here we are. The laboratory in which I work is being founded in 1993. From that moment, we work hard on different fields of robotics. Then we move in a consortium with other university. It's called Consortium Create, and all our works also brings to the born of an innovative startup a few years ago that is called Robotics, and in which we mainly focus on inspection and maintenance. The CEO is one of the full professor of my group that is called Vincenzo Lippiello. So in Prisma and in Naples, we work on different areas of robotics. Among them, that is human-robot interaction, surgical robotics, soft robotics. We work on aerial robots, mainly with aerial manipulation task. And in fact, starting from 2012 to here, we had found in the different research projects from a European Commission. We participate every year to this very well-known competition in Europe to be involved in these research projects. Among them, 7 projects were founded in aerial projects. And in particular, 4 of them in inspection maintenance with aerial robots. This also motivates our work and make us think that aerial manipulation for inspection maintenance is a very hot topic, both for industry but also for research. Along with the research program, of course, we have collaboration with other company, like a very well-known any company. So what is IR Robotics? Mainly, everyone know quadcopters, hexacopters, or also other kind of device that in last year they became very famous for also in the field robotics. Of course, this is thanks to their capability of surveillance, monitoring, search and rescue. They can fly very fast, very quickly. Mainly what happened, probably starting also from Amazon, was the idea that this kind of tools were also able to modify the environment. In fact, Amazon, but also other aerial robotic company started to work in object transportation, and in last period also in human transportation. So this also make us think that aerial robots can also modify the environment. In particular, we can define the aerial manipulation as the branch of aerial robotics in which the robot can also physically interact with the environment, like a classical mobile manipulator that is not placed on the ground, but can also fly. So in particular, we can have different kind of aerial manipulators. So we can consider also just a pole placed on our aerial robot, or something of very more complex, like a multi-degree of freedom manipulator, as we will see in this presentation. However, as main elements, an aerial robot is composed by a floating base that is classical unmanned aerial vehicle, plus something that allow him or it, let's say, to interact with the environment, to modify it. So a gripper, an hand, and so on. The first example of aerial manipulation that we recognize in our group is being made with the Centro Avanzato di Tecnologia Aerospaziale in Seville. It's a very well-known, famous center in Europe, in which they, in the project ARCAS, what we try to do was to mount some structure with this bar. So the goal of the robot was just completely autonomously to fly closer the object to manipulate in order to perform a very basic, simple operation if you consider a classical industrial robot that are that activity of picking and placing. However, with the aerial manipulator, everything is more complex because, of course, we have a floating base. We have to consider several other stuff, among them the battery duration of this kind of device. And this project was quite old because it started in 2012, so several years have been passed. What happened in the next step is that this project has been followed up by another project called Aero Arms, in which we just moved this technology on something that was really more complex. As you can see from this video, a classical octocopter, so a classical UAV is bringing with him an industrial robot. This is a KUKA lightweight. Its weight is almost 14 kilograms. So we move this from an indoor scenario, so very controlled scenario, to an outdoor scenario with an high payload capability, and this also open the path to several other possibility. But until now, we just spoken about the possibility to manipulate the environment. What's for us is much more interesting is the possibility to perform this NDT measurement. Let's see what is a measurement like this. NDT is it is a set of techniques, non-invasive techniques that are used to check the quality, the internal quality of a material in order to assess how that structure, that material internally is composed. The goal is to search if there is internal decrease, internal crack of the material that in future can also bring to accident, let's say. There are several methods to perform this kind of task: microwave, visual, acoustic, or for us much more important is the ultrasonic measurement. As you can see in this picture, with an ultrasonic probe, we can just use high frequency sound waves that are introduced into the material, and just checking the time of flight of this data, understanding if the material, the thickness of the material is as expected or is corrupted inside. Consider that this kind of tests are every day made, not only in industrial facility, but also in the civil environment. So to check bridge, to check also building, and so on. One requirements needed to perform a good ultrasonic measurement is that the probe, the ultrasonic probe that we want to use to of course, we can see here again in IR Arms project. Also, this platform has been made by the Centro Avanzato di Tecnologia Aerospaziale in Seville, present probably one of the first platform that is able to in a semi-autonomous way to perform this kind of measures. You can see here the checking of a bridge. This is very important, especially in that nation like sadly also Italy, that has a lot of very old infrastructure that must be checked every time. You consider a bridge that is placed in altitude, you have to mount a set of scaffolding is also risky for human life. So we need for sure from industrial, from research, from business point of view, a way to check it's very in a very easy way and a human safety way, first of all. This is another platform. This is being developed by us at Unina with the help of the robotics startup. The concept is very similar to the previous one. However, in the previous video, we've seen a simple stick plugged on the UAV. Here we have a classical octacopter, coaxial quadrotor that is equipped with a 6 degree of freedom arm, and the test here is to stay in a stable contact with the environment to perform the thickness measurement. So here we have something on the very a complex machine that is a real aerial manipulator. With this, we can also check in all the direction the thickness of a building and so on. So let's move in something that is much more interesting for us. We have seen that this kind of device can be used during the flight, but what happens if we want to check, to assess the quality of material of something of more structure like the oil and gas pipelines, as you can see in this slide. Such pipelines actually represent a very vast network of pipes that are used everywhere in the industrial plants, but also in the city to transport elements like hot water, but also hazardous liquid gas and so on. Okay, what happens is that if the internal corrosion of these pipes, so the variation of the thickness of these pipes is too much, this could also bring to dangerous situation like explosion or similar. So what happened is that these kilometers of pipes must be inspected frequently. Typically, these pipes are also placed on altitude in pipe racks that are placed in altitude to allow also more easy access and also to preserve the ground space. So what happens is that the work of inspecting this pipe it's very expensive. Not only from the time point of view to inspect all this kind of structure, but also from an economical point of view, because we have to mount several scaffolding. The industrial plants must be stopped during the operation of the human operator and so on. So actually, these are results of iFlyer project, again, an aerial project, an aerial research project, in which we have tried to solve this problem with an hybrid platform that is able to directly land on the pipe and use a mobile base to move along the pipe and also inspect the surface thanks to again a lightweight arm. So this platform built again here in Naples is composed mainly by three components. The first component, we have the aerial platform that allows the robot to fly. It's an hexacopter and each frame with the two line of motors. This solution has been adopted in order to resize at the maximum the overall size of the aerial robots, also to navigate in narrow space. thanks to the battery, we were able to fly up to 20 minutes with a standard autopilot. Then we have the mobile base that is composed by a carrier module with 4 active omnidirectional wheels that allow the robot to navigate the pipe after land and also to be stable on the pipe, rotating around it. And finally, we have an anthropomorphic arm. Why we consider very novel and interesting solution this one? Because instead of having an arm that must be placed in all the position to check, this end effector is able to completely wrap the pipe in order to inspect both the upper side and the bottom part of the surface. Okay, we actually tested this in an industrial mock-up at again here in Naples, with a classical flight as already said, controlled in sense that here we are using a MOCAP system to stabilize the robot. However, the robot is endowed with all the classical sensor, vision sensor, and GPS, and so on. And after landed, the manipulator is unfolded in order to wrap the pipe and perform the inspection thanks to a circular path that bring the manipulator also to check the bottom part of the duct. Okay, so this hybrid solution is very innovative and it preserves also the battery duration of the whole system because, of course, when we have landed, the propulsion system of the avionics of that we know is it's very consuming by the battery point of view, it's directly shut down. So we can operate also for hours. Of course, there are several open challenges to bring a real aerial manipulator in an industrial plant because this kind of facility require, of course, something that must be assured, like the compatibility with the ATEX standards, redundancy in order to cope with sensor fail, and also the possibility to have a certified solution. What is needed, of course, is a lot of work. We are mainly working right now on the implementation of robust controller to stay in fixed contact with the environment and the possibility to use also classification autonomous method to predict the corruption of the internal material.
Maybe a little bit of background before we start. So I also come from technical background. My PhD was actually in aerial robotics. And I work in a laboratory where we have been developing different types of robots. We pride ourselves in the fact that our robots are driving, walking, jumping, and working together, and of course, flying. So we take, of course, inspiration from biology, human nature, and we work a lot with industry. So a lot of our applications usually are founded by what our industrial partners require from us, and they want us to solve a particular problem and to make their lives easier. So I will actually go a little bit lower level than Jonathan did, in the sense that I won't be talking that much about maintaining contact with UAVs, but in this workshop, we want to ask ourselves the question, can we do things better? So this image here actually sums up where UAVs are used right now, but in a complete, let's say, manual way. So what's the problem here is that manual operation of UAVs is a burden for the operators. It's sometimes working in very harsh environments, especially, for instance, in offshore wind farms. And it's a tedious job. So it's obviously something that can be automated and make the operator's life simpler, ranging from farms all the way up to infrastructure inspection. And Here you see a video of a typical inspection of bridges done with UAVs in a manual way. You have a couple of operators. You have to close down the bridge still for safety reasons. This was actually filmed in Dubrovnik a couple of months, well, actually a couple of days after the lockdown from the COVID. So it was pretty much empty. It's the only chance in the world you'll get in Dubrovnik where there's nobody there, no cruiser ships, and you can perform inspection. But it's not simple. The infrastructures are large. They have a lot of metal inside them, which obstructs which produces magnetic interference, and your compass doesn't work. So you have to fly. You have to take off from somewhere else and then fly to the bridge and lose time. And the operator has to move around. So it's actually not that simple as you would say. Pick up a drone and have fly around and take pictures. So if you want to make it better, what we actually want to be able to do is to localize the UAV autonomously. So this is why we need a lot of equipment on the UAVs, LiDARs, cameras, and we actually use them to collect point clouds and then try to recognize and match these parts of the infrastructure that we want to take image of, and then do it completely autonomously. So this here example of the bridge in Osijek, also in Croatia, this inspection has been done autonomously, and we've been using LiDAR to detect certain parts of the bridge, and then we can match the images to that particular part and produce one-on-one match to the actual inspectors to see if the bridge is in the good shape. But okay, so can we do something else but not just taking pictures? And actually, one good thing that you can optimize is measuring the natural frequency of the infrastructure. So each house, each building, each bridge resonates on its own frequency, and it's actually part of the regular maintenance to inspect that frequency and see if the frequency changes. That means that there are some problems in the infrastructure. So how this is done now, you manually have to vibrate the parts of the construction. You see this this hanging bridge also in Dubrovnik, so the part of it is vibrating. This is actually induced by the human down on the bridge, and that vibration over here can be detected in an image, and finally this can be used to measure the frequency of the bridge. And we were actually able to measure to a dime at the precision that they are currently measuring it, using very expensive equipment with accelerometers, and placing them on different parts of the bridge to make sure that they can actually measure these frequencies. So, and we were actually able to do it by autonomously flying with the UAV, stabilizing it in the air, and measuring the vibrations through the map, for the image. And one good thing about it is you can completely automize it in the sense that this is perfect conditions. You have clouds, you have background of sun, something that's quite simple and structured, so we can actually move straight from the simulation environment that you can see here, where we measure the vibrations and then we tune our algorithms, and then move directly to the site, and we can still measure without any modifications to the algorithm, which is actually something that people that take problems from the laboratory to real world experiments know it's actually quite tedious. But a lot of the situations in infrastructure is with UAVs, you're facing the clouds, you're facing the sky. So it's quite easy to model it and move directly from the lab to the actual on-site experiments. So speaking of laboratory experiments, continuing on what Jonathan said, so one of the key aspects and issues we're trying to solve as researchers and developers of new technologies, how to stabilize the contact with the environment. So to apply pressure, interact with it, and do something smart with the UAVs, not just observing stuff, but actually interacting with the environment. So one of the things we can do is we can actually, what we propose is using a team of UAVs to place vibration sensors on the bridges in order to have inspection, continuous inspection. So if you combine the localization with respect to the map of the infrastructure, then we can actually plot places where we want to put the sensors on, and then we can have a team of UAVs working together to place it. So you can imagine one UAV can go and place a primer on the spot, and then move so that another vehicle can come, fly up to that place, localize this primer, and then attach a sensor on it. So the idea is actually to do it sequentially on the whole bridge on different spots, and then combining multiple vehicles flying at the same time doing different experiments. So there's a lot of mission planning here involved, and of course autonomy is one important aspect. And once you apply the primer, you want to be very precise when you apply the sensor on. So we can use onboard sensors to detect where the primer is, move to it, and then attach. If you like, I have a lot of QR codes down here. You can scan them to check our laboratory experiments done so far. But we are looking forward to moving this to real applications. And then, okay, this is all very expensive work, and infrastructure costs money, and companies can actually afford to build autonomous systems to perform inspections because they have to do it regularly. But can we do it for personal applications? Can we actually have, go to your local store, buy a UAV, and then apply certain technology on it to, let's say, measure your house for renovations, to see if you're losing energy, to measure what can you do to improve it. Build an information model of your house, you send it to a platform, and then this platform actually calculates how much money you're going to save if you change the windows, if you move to a different type of heating device, etc. So this is actually a part of an Encore project that we're collaborating on, and we're building this part where you actually want to have your regular off-the-shelf drone. You buy it, you apply the technology with it. You take images, you inspect the parts, and then combine all of these data into building information model. You upload it to the platform, and then this platform provides you with the best option for your renovation. Moving on to infrastructure, here is the video of wind farm inspection. So this is another tedious job, and a lot of times you work in very harsh environments. So we collaborate with a company called Helvetis. They're a Swiss-based company that provides inspection, I think, for the majority of offshore wind farms in the world. And they know how problematic this task is, because when you go offshore, you need to rent a boat. You often work in very harsh conditions. It's extremely hard to train pilots and have them work continuously to inspect multiple wind farms. So what we're trying to do to help them is actually to perform this in a fully automatic way, to automate the procedure completely, and in this way make their life easier. So how do we do it? Again, learning from the things that we know from inspecting bridges, We can also learn to localize with respect to the shape of the wind farm. They're usually quite easy in their 3D model. It's quite similar all the way around. So key features can be used to localize the drone quite precisely, autonomously, and then have it inspect and bring back the data, or send it to the cloud where it's actually processed. And the good thing about it is when you have this precise localization with respect to the 3D model, you don't rely on the post-processing to stitch the images and to get a 3D model of the wind farm here. No, you can actually use the information on where you are to stitch the images in real time, and then when you fly down, you can actually point to the parts of the wind farm and see what's going on there and if it's okay. So just because I stole your coffee break, I think I have to keep it short. So I will take your questions, and thank you for your attention.
So I hope you can see my slides and you can all hear me. Perfect.
All good. Yes.
Great. So thank you very much again for inviting me for this talk. I'm really happy to be here. I am a computer scientist, as Aneli also said, and have a PhD in mechatronics. I love technology and enjoy talking about the future and emerging technologies. My research work aims to provide data solutions, methods, and methodologies to aid decision-making generally. And it focuses on challenges on interoperability, sustainability, and complexity related with cyber-physical systems. And they generally comment on technical solutions and suggestions on integrating these systems with each other, assessing their performances, and suggesting ways to dealing with their complex nature. Yet today's talk will focus on a design of cyber-physical systems, underline the importance of data-driven approaches, and criticize the current engineering practices. Because more than being a computer or data scientist, I'm also a concerned citizen who cares about the world and the nature. I'm a teacher who wants to give new tools to the next generation to deal with the new world that we are building one system at a time. For that reason, my life is full of dilemmas. On one hand, I want to use data and new technologies. On the other hand, I get disappointed when they are not designed for all of us to benefit from them, or the social implications of them are not considered. I want more integration, more interaction, more insights, but I don't want equality, diversity, inclusivity, or ethical concerns just to disappear. So today I want to welcome you all to my world. I will firstly remind us how we have come to this point by presenting a brief history of industrial revolutions. Then I will introduce you a few examples of cyber-physical systems, so we know what we are talking about. And we will talk about this weird thing called data and try to understand how we are treating it. And we will look at some of the dilemmas around data, and hopefully I will have enough time to tell you what we as individuals, institutions, or organizations can do to navigate better in this new world by introducing a few principles and the favorite 3 mindsets of mine. So let's start with a short history and look at a series of industrial revolutions that changed the world. The first industrial revolution was essentially started when we discovered how mechanization, water, and steam power can help us to do all kinds of interesting things, really. Then from the late 19th century into the early 20th century, mass production, assembly lines, and electricity advanced manufacturing and production. This enabled a widespread adoption of technological systems. We call this technological revolution. Later, at the beginning of 1950s, the third industrial revolution brought semiconductors, computers, and automation. This is the digital revolution. Today, we are experiencing the fourth industrial revolution. We have interconnected systems throughout the networking technologies. It's evolving at an exponential rather than a linear pace, and it is disrupting almost every industry in every country. This new era is cyber-physical systems driven. These systems are integrations of computations, networking, and physical processes with feedback loops, where physical processes affect computations and vice versa. Cyber-physical systems are already part of our lives today and will be there in different forms in the future. I have chosen a few examples that I had chance to work with. They come from different industries, so it can be nice to see how diverse these systems are. One example of cyber-physical systems is integrated transport systems. Essentially, what this means is sharing information between different modes of transportation systems, including autonomous vehicles, such as cars and drones. Another example is perhaps most interesting one for today's topic is robots. In this case, autonomous warehouses, where different types of robots collaborate to fulfill some supply chain related tasks. We can give another examples of robots collaborating for inspection and maintenance purposes also. So when we have several robots and we want to integrate them to inform us to make better decisions, then we call this integrated system as cyber-physical systems. Other examples include smart factories or smart cities and infrastructure, where they could also include different forms of systems, including robots. As you can see, these systems have a few common characteristics. They are connected, they are autonomous, and they are intelligent. And all these abilities are possible because today we can collect, store, and analyze huge amounts of data that we were not able to do before. After working with these systems for years, I have learned a few things, and today I want to share with you some of them. One very important lesson that I learned is about data. Many calls data as the new oil. I hope that we can find a better metaphor and create a brighter future direction for data. Even though the oil-driven revolution fueled many industries and helped the world to advance, the waste of this revolution, the greenhouse gases, and the effects on climate change is the biggest problem that is threatening the future of this planet. When we look at some instances, even the very mature technology providers who are leading the data-driven revolution are having difficulties to deal with the challenges around data. As a result, chatbots are turning to racists, autonomous cars are running red lights, and many are spending incredible amounts of investment and time to short-term solutions. I will try to explain 5 dilemmas of data that I come across a lot when I was working with cyber-physical systems. I believe that these are also some of the root causes of these unfortunate events. The first one is about collecting data, but in a sustainable way. Collecting enough data while considering the privacy, security, anonymity. Storing the data, but not consuming tremendous amounts of energy. Currently, we are collecting everything, but not really using the data. It may sound surprising, 80% of the collected data that we have in our industries is unstructured, and 55% of that one that is called so-called dark data that no value is driven from. The second dilemma is more about sharing data. This surprises me a lot, especially industries and organizations that are not fully digitalized yet. These questions around sharing data is always one of the last questions that people ask. Who can I share my data with? How can I share my data? How can I make my data available to others? How much? How long? Sharing or no sharing? The real value of cyber-physical systems, which will make the world hopefully a better place, cannot be achieved without interoperability. And interoperability, which means integrating systems seamlessly, is not possible without sharing. Trusting data is another example. We want to use data and learn from it, but can we really learn from data without checking the quality of it, being aware of its biases? One cannot trust the results if we don't know the limitations of data. This includes considerations related to responsible data and ethical use of it. Volume of the data is another problem, kind of an old problem really, yet it is still valid. Not only high volume of data is very resource intensive, but also sometimes narrow data sets are more efficient and effective, even more informative than complex big data sets. Today we are building systems without creating well-taught data models. Last but not least, the role of humans in a highly intelligent, data-driven processes is an important point to make. How much to automate, for whom, how long, how to control the automated decision-making through, for instance, artificial intelligence and data. This part is going to be vital for the next generation systems, and our current engineering practices are not even close to have necessary frameworks to deal or to consider this. We can tackle these dilemmas and challenges by building structural change that will help us to get the most out of our data. As data has its own limitations, engineering discipline as a whole, we, our organizations as individuals, we also have similar limitations. To be able to exist in this new world, we need to reconsider our organizational structures. Data should be at the core of the organization. We should think about how to collect, curate, integrate, and analyze this valuable resource. This should include providing continuous skills development programs for everyone to increase the ability of individuals. We need to improve our digital capabilities, as well as change the culture and improve the adaptability of our organizations. We should be able to try new approaches, new technologies, new tools, instead of waiting for a perfect tool to arrive. Now, we know very well that the most of the learning happens when we try new things, regardless if the resulting system fails or succeeds. This perspective to allow people to learn new skills and try new things may help to develop data and technology fluency that most of our organizations are needing very urgently. We should create better processes and well-defined data procedures to manage the data, which could help us deal with the dilemmas that we were mentioning just a few slides before. We need to consider more sustainable ways to work with data, build better data models to do not collect unnecessary data, and certainly be more mindful about data privacy, ownership, similar rights of individuals. Our processes should not lose the whole when we work on smaller parts. They should be aligned with this bigger picture. Cyber-physical systems are highly technological systems, but they interact with people, and the social implications of these interactions are as important as the technical aspects. And lastly, we should start to shift our mindsets. A new mindset for an engineer, for a developer, a new mindset for an organization, a new mindset even for a scientist and all of us. This last point is perhaps the most important, but least technical one. Before concluding this talk, I want to talk about this last point a bit. We have discussed the brief history of at the beginning of this talk and talked about how interconnected this new world is. In this interconnected world, change is occurring ever more rapidly, and the boundaries between industries are blurring. Cyber-physical systems are expected to not only take smart decisions, collect sustainable data, drive better operations, but also be part of systems of systems or ecosystems. This is quite new and challenging for our traditional engineering practices. That's why we need a shift. What do I mean by shifting our mindsets? I believe that many technology or data-related issues that we have discussed are more than only technological problems. Most of the challenges around the data can be solved with already existing tools. But unfortunately, our organizations are not able to ask the right questions to find out the right answers. And the ability of asking right questions depends on many factors. We will briefly go through 3 mindsets and 3 ways of thinking: systems mindset, design mindset, and futuristic mindset, and explain, or I will try to at least explain, how they can help us to deal with the challenges we are facing today. If we agree that the 4th industrial revolution is here, and it is exponentially growing, if we accept that the future will be cyber-physical systems driven, intelligent, autonomous, and connected, we need to also accept that the world is full of connected systems of systems. When dealing with interconnected systems, understanding the whole system and the dynamics between different parts of this whole is vital. Systems thinking is a great methodology to deal with these concerns. In systems thinking, we consider how the behavior change. We look at different patterns, structures, and mental models, identify causal loops and connections. We move from disconnections to interconnections, from linear thinking to circular thinking, from silos to emergence. And we value the relationships and synthesis more than isolations and analysis. If we can understand this systemic perspective and acquire systems mindset, we can discover a lot of opportunities when it comes to these smart future systems. To be able to ask the right questions, we need to provide an environment that we hear the problems. And we need to be able to listen. The other important new perspective for cyber-physical systems design is the human-centered design. Our current engineering practices are traditionally requirements-driven, and the user experience is very far end of the process. Cyber-physical systems are certainly product of interdisciplinary efforts, and we are getting used to that. We should also make it part of our processes to include users early in the process, because users' experience matters. We should start to design our cyber-physical systems with people, for people. Design thinking methodology can help us to do this. The design thinking methodology reminds us that we should always start with the why question and encourages us to empathize with the users of our systems before even defining the problems. Sometimes we lose track of putting the people at the core, at the center of our cyber-physical systems design, because we focus on a specific new technology. Technology is a tool. It is not the goal. Similarly, data is a journey. It is not a destination. As we already saw with the fossil fuel example, many of the problems that we are dealing today were the solutions of yesterday. We need to stop this vicious cycle. We need to act different. We need to be able to take a step back and see how different technologies, different trends, different solutions and decisions may affect the future. We tend to think that everything is changing at the same speed. Yet we have experienced far many times how in this interconnected world, directly can turn upside down only with one event. I mean, look at the effects of pandemic. None of us were prepared to this. We know that the cyber-physical systems will share data with each other through new ecosystems. They will contribute to make world even more connected by enabling the device level, embedded systems level connectivity. Wherever we have ecosystems, we have complexity, we have chaos, and we have unpredictability. Therefore, we should always have this future perspective in mind to detect the threats, opportunities, and prepare different strategies for unexpected situations. These mindsets has the potential to help us to understand how the world is changing. We are all contributing to this change by research, by teaching, even by small conversations, building stuff, attending meetings, and all. My experience in studying the future intelligent systems taught me the importance of the big picture. We cannot give same education, use same processes, focus on same problems, do as usual, yet expect different outcomes. We all need to be systems thinkers, design thinkers, and futurists, observe this rapidly changing world, listen each other's perspectives, and position ourselves to make the best future possible. I would like to thank you for listening, and I'm happy to answer any questions you have. Thank you.